The life of an EV battery can drop by more than 50% if it's not kept within its allowable temperature limits. And that's not even considering safety risks like thermal runaway, the kind of failure no engineer wants to see. Hello everyone, I'm Ankit Naik, Applications Engineer at Wolfram System. In this session, we will explore how thermal management in electric vehicles work and how we can model and optimize it using Wolfram System Modeler and the Wolfram language. Thermal management is one of the critical, if not the most critical, regulatory systems in an electric vehicle. Its main job is to remove heat from different parts of the vehicle, the motors, inverters, batteries, and other components, and prevent excessive heat buildup. Doing this will directly improves efficiency and range because the less power we spend on cooling, the more energy goes into driving. At the same time, a good thermal system can reuse heat, for example, from the battery or motor instead of wasting it. Of course, safety is another key objective. The battery must be kept within its safe operating window to avoid degradation and prevent thermal runaway. And finally, there's passenger comfort. Whether it's a snowy winter morning or a 40 degrees Celsius summer afternoon, the cabin has to reach and maintain the desired temperature quickly. So, as you can see, this system faces very wide and sometimes conflicting requirements, which makes it one of the most complex subsystems in an EV. In this talk, we will focus on one critical part, the battery cooling system, and explore how its subsystems can be modeled, optimized, and tested for new designs. For today's presentation, our goal is simple. Keep the battery between 20 and 40 degrees Celsius. We will design a thermofluid circuit using components built in Wolfram System Modeler. And we will assemble it step by step. Starting from a basic cooling loop, then adding a radiator, a heat pump, and finally cabin integration to reuse heat. The image you see here is where we will end up. Let's build towards that and see how each addition improves control of the battery temperature. Let's start with a battery connected to a coolant loop. Here you can see the pump driving the coolant through the circuit. A three-way valve splits the flow between the bypass line and the battery branch. The coolant enters the battery through pipe 3 and exits through pipe 4. There is also a check valve that prevents backflow into the bypass line and a reservoir that maintains a reference pressure in the loop. The input signal Y controls the valve opening. When Y is equal to 1, all coolant flows through pipe 3 into the battery. When Y equal to 0, everything bypasses through pipe 7. You might be wondering what these components look inside. Let's switch to System Modeler to explore the model and run a quick simulation. For anyone new to System Modeler is a graphical modeling environment for building dynamic multi-domain systems, from electric vehicles to power grids. What you're seeing here is a model center workspace. The battery component, for example, is built using standard blocks from the built-in Modelica standard library. If I double-click the battery, we can look inside it. It contains a pipe carrying the working fluid, a constant heat input representing resistive losses, and a heat capacitor body that stores heat and exchanges it with the coolant by convection. Similarly, you can open the other components to see how each is constructed. Now let's simulate the model and test different parameter settings. When I click the simulate button, it opens Simulation Center, where we can access all model variables in real time. Here, the simulation is running live. We can change parameters and immediately see how battery temperature responds. Let's see what happens when the valve opening is 0. All the coolant flows through the bypass line and the battery heats up rapidly due to trapped heat. As I increase the valve opening, more coolant passes through the battery and the rate of temperature rise slows. But the temperature still continues to increase over time. If I increase the pump flow rate, we start to see the battery temperature drop. However, if we let the simulation continue with the same settings, both the coolant and battery temperatures still drift upward. Why is that? Because our loop has no way to reject the heat that's being added. Let's get back to our presentation. In Wolfram language, you could also see the simulation results of the model. You could also create dynamic diagrams to see the animation in action. You could see with time the color of the pipe changes, showing the temperature is increasing with time. To remove this accumulated heat, we need an additional component, a radiator. Let's add one to the model and see how that changes the behavior. In this version of the model, we now have added a radiator and a bypass line around it. Valve 1 controls the coolant flow from the radiator into the battery circuit. Let's open System Modeler to take a closer look at how the radiator is modeled. If I double click on the radiator component, we can see two circuits inside. On the top, the coolant line, and on the bottom, the air circuit with air flowing from left to right. The ambient temperature parameter defines the inlet air conditions, and heat transfer between the coolant and air is represented using a convection component. This is a simplified yet effective way to model a heat exchanger. System Modeler also includes more detailed high-fidelity radiator models with fin geometry and parameterized correlations. But for this study, I will keep it simple. One thing to note before simulation, we currently have only one pump in the loop. So if valve 1 is closed, coolant flow through the battery essentially stops. Let's simulate and vary the two valve openings. With both valves closed, the battery temperature rises steadily. There is no cooling path. When we open the radiator side valve, flow increases through the bypass line. But the battery temperature doesn't change much because coolant bypasses the pack. Now, as we open the valve to the battery, coolant starts circulating through the pack and radiator, and the battery temperature begins to fall. The coolant temperature also stabilizes or even decreases slightly as heat is rejected to air. In a real EV, we would now introduce a PID controller to automatically adjust the valve actuators and keep the battery temperature within the desired 20 to 40 degrees Celsius range. Let's return to the presentation and analyze how the valve position influences the overall cooling performance. To do this, I performed a parameter sweep over both valve openings and recorded the battery temperature at the end of each simulation. We generated all combinations of valve settings, passed them to System Model Simulate, and ran the simulations in parallel, and finally collected the resulting temperatures to create this contour plot. But what can we learn from it? If we want to heat the battery quickly, we should keep the radiator valve and the bypass valve closed. minimizing heat loss from the battery to the environment. If we need to cool the battery, we open both valves, increasing flow through the radiator. This kind of insight is exactly why integrated modeling is powerful. It connects system architecture, control logic, and thermal performance. Keep in mind though that this plot is valid for a specific ambient condition and current circuit layout. That is the circuit that contains one pump, two valves, and the given flow paths. So the next question is, what happens when the ambient temperature rises? When we simulate the model at different ambient conditions, we find that as the outside temperature increases, the battery temperature also increases, meaning the radiator alone can't reject enough heat in warm climates. To handle that, we will need to add another component, a heat pump, which can actively extract heat from the coolant even when the air is hot. What you see here is a heat pump linking the battery coolant circuit with the radiator circuit. A heat pump's job is to move heat from a low temperature source to a higher temperature sink. It draws in electrical power and uses that energy to transfer heat, not generate it, which makes it far more efficient than simple resistive heating. In our model, the battery loop acts as a low temperature side, while the radiator loop is a high temperature side that rejects heat to the ambient air. We now also have two separate pumps to control flow independently in the two sub-circuits. One circulating coolant through the battery and the other through the radiator. Let's look inside the heat pump component. In this simplified representation, I take the electrical power input and multiply it by the coefficient of performance, that is the COP, to determine how much heat the system can move. The model then divides the energy flow into two parts. The heat is absorbed from the battery coolant loop and the heat is rejected to the radiator loop. Of course, there are more detailed ways to model this, for example, using compressor maps from manufacturer datasheets or a full vapor compression cycle model with the refrigerant states and expansion valves. But for today's study, however, this abstraction is sufficient, since our focus is on a system level behavior rather than the refrigerant dynamics. Now, let's repeat our parameter sweep over ambient temperatures to see how the system behaves. Unlike the previous configuration with only a radiator, you can see here that the battery temperature remains almost constant across different ambient conditions. That means the heat pump is effectively regulating the battery temperature, maintaining safe operation even when it's hot outside. We can visualize this further with an animation of the circuit. The simulation begins with both loops at the same temperature. The pipes appear purple. As time progresses, the radiator loop heats up and rejects the heat to the environment, while the battery side coolant stays at a steady temperature. In other words, the heat pump is doing exactly what it's meant to, that is extracting heat from the battery loop and dumping it into the radiator loop. But this raises an interesting question. In winter conditions, when we need heating instead of cooling, could we reuse the same heat to warm the passenger cabin rather than waste heat to the air? Of course we can. Let's add a cabin space component to the model and see how this recovered heat can be used to improve passenger comfort. In this circuit, I have now added a cabin space heating loop in parallel with the heat pump circuit. We introduce a new valve 3 which controls how much coolant is directed towards the cabin. When valve 3 is 0, the valve is fully open towards the cabin and the coolant bypasses the heat pump. When valve 3 is equal to 1, the flow to the cabin is closed and the coolant circulates only through the heat pump. Now let's look inside the cabin space model to understand how heating actually works. The upper loop is a coolant circuit, just like before. The lower loop is an air circuit where air enters from the ambient and its flow rate is controlled by a fan. As the air passes the heat exchanger, it absorbs heat from the coolant through convective transfer, warms up and flows through the cabin volume and finally exits back to the ambient. In a real vehicle, this air loop could typically include auxiliary electric heaters or a small chiller in series to fine-tune comfort levels. But for this study, we will keep the focus on the thermal reuse behavior. So, how does valve 3 affect cabin temperature? Using the same workflow as before, I simulated the system for a range of valve openings and plotted the final cabin temperature after 100 seconds. And here's what happens. When the valve is fully closed towards the heat pump, almost all coolant goes through the cabin. But since the radiator loop doesn't warm up, the cabin doesn't heat effectively. As we slightly open the valve, a portion of the coolant passes through the heat pump loop, which raises its temperature. The hotter coolant then transfers more heat to the cabin air, giving us the maximum cabin temperature. If we continue opening the valve further, more flow bypasses the cabin, so less heat is available to it and the maximum temperature drops again. This single sweep helps identify the optimal valve position that balances coolant distribution between the heat pump and cabin to maintain comfort without wasting energy. So now we have gone full circle. We started with a loop that only removed heat, and we have arrived at a system that can actively manage and reuse heat, improving both range and passenger comfort. The components we have used today come mainly from the thermofluid library, a versatile library that combines thermal and fluid characteristics. But of course, System Modeler supports many other libraries that provide more fidelity or focus on specific domains. For instance, the Modelica Fluid Library offers a detailed representation of flow characteristics and heat transfer, including compressibility, turbulence, and advanced wall heat conduction models. The Hydraulics Library contains components designed for oil and hydraulic systems where pressure dynamics plays a major role. The IBPSA library, developed by the International Building Performance Simulation Association, focuses on building energy systems such as HVAC, chillers, and air handling units. The Thermofluid Stream library uses a different mathematical formulation for the handling of pressures, leading to linear, numerically easier systems, particularly useful for large fluid networks. And finally, there are many third-party Modelica libraries, both open source and commercial, that cover specialized domains from aerospace cooling and power plants to microgrids and chemical processes. To summarize, in this presentation, we walked through a complete workflow for modeling, simulating, and optimizing systems using Wolfram System Modeler and Wolfram language. We explored a thermofluid circuit designed to keep an EV battery within its safe operating range, and along the way, we studied the key components, which are the radiator, heat pump, and cabin space loop, to understand how each contributes to thermal management. Through simulation, we saw how these components interact, how parameter sweeps can reveal system behavior, and how the integration with Wolfram language and System Modeler helps us move seamlessly from modeling to insight. I hope today's session gave you both a motivation and practical understanding to start creating your own thermal management or fluid circuit models. And remember, the same modeling principles apply beyond electric vehicles, like to HVAC systems, microgrids, industrial processes, and energy networks of all kinds. Thank you for your attention. And now let's open the floor for questions.
Yes.
So there is one question by Harald, like the check valves in the cooling circuit confuse me. The way they are drawn, they only admit upward flow. And Harald, you are right. I think I made a mistake when I was drawing the icon over the check valve. It should be other way around. So you are right to identify that the direction of the check valve was not right. I will fix it. Um, Sojit, do you have any other questions for me regarding the
Uh,
talk?
not that I can see. I noticed that you right. So if I understand correctly, the way you were optimizing is by performing several simulations with different parameter values, right? And then
Yes.
plotting and then visualizing. Okay. Mhm.
Yes, plotting the final value like after a simulation of 100 seconds.
I
Uh,
see.
s- right. Of course, there are multiple other ways. Like you have the system model uncertainty plot, where if you want to have distributions for certain parameter values, you can do that as well. But I thought just a simple parametric sweep, which showcases that one can do multiple simulations in parallel and then combine all the results together to get the nice output, was good
Hmm.
enough
No, no, for
for
sure.
my presentation. But of course, there are uh,
Mhm.
many cool things you could do.
Yeah, and many approaches for optimizations. I think this is perfectly fine.
Yes, yes.
Uh,
Uh, I was also inclined to add the system model validate requirements. Like once you have a thermal circuit like that, there
mhm,
are several requirements on the circuit. For example, the battery temperature should not exceed between X and Y, and the cabin temperature should not be below, let's say, 20 degrees Celsius and not be above 25 degrees Celsius. So there are
mhm,
various requirements, and we in the last release we have this system model validate requirement function as well, where we could
mhm.
specify those. But I thought you were giving a talk specifically on that, so
Right.
I thought let's skip that as well.
Yeah. Right.
Yes.
That
So
that
so
is that is that is some things to talk about in the other presentation. Yes.
yes. So I think I will then, as we have no questions, I will then conclude by pointing the audience to two different talks. The first talk is on how we can use system modeler to train AI models. That is just next after this session. And
Mhm.
then there is another talk by you, Sergio, tomorrow on how we can specify requirements so that we can automatically validate models uh, for uh, for different conditions.
Right. Right. I just noticed that there is one last question. It's how do you put an infinite time into the simulation?
Yes. So
Mhm,
uh, for yeah, so there are two ways. If we simulate in real time mode, then so when you simulate there are two ways you can simulate a system model model. One is by defining the time range, and then the solvers, they automatically uh, identify how things needs to be solved, and for that we need the simulation time. But if you simulate the model in real time mode, then you can specify a infinite time. There is currently uh, no way to define the infinite time uh, for normal models, system model models. Sergio, do you have any good answer to that? Maybe by using Mathematica, one could do some cool, some intelligent stuff there.
right. No, I just wanted to mention that, yeah, so you can just always check into the simulation settings, and then there is always the possibility to um, add like an infinite time in the stop time, if I'm correct. Um,
Yes, but I think people are just thinking of like what would happen if like the asymptotic behavior and things like that.
I see. I see.
Possibly, uh,
All right.
currently we don't have any such things, right?
I see. I see. And yes, for the synthetics, yes, you're right.
Yes.
Yeah. So I guess we are uh, good to go. So I'm gonna join the next presentation because that's I have to jump into the next one. Um,
Uh, so there's a comment that this was mentioned during the presentation of new on system modeler things. Uh, I think you might be confusing this with the calendar time updates to the simulation plot. So that is new in 14.3.
right.
So rather than having times in seconds or hours, you can specify a calendar start time and then have the x-axis as a calendar time scale. But at least I am not aware of this. So
Yeah,
yeah,
or there's also a possibility that he is referring to the validation or maybe another of the features. It's a little bit
yeah,
there
yeah.
are,
Okay.
but we're gonna have more presentations, and there is also the possibility to join us in the after hours where we're
Yes,
gonna
of
talk.
course.
So yeah, so
Yes. So if there are any questions that remains unanswered, or
mhm.
you want some further clarification on the something in the presentation that we have missed, then we have an office hour uh, that you can join and you can ask us questions there.
Yeah,
Right. Okay then. So Sergio, let's
yeah,
head back. Let's move to the next presentation then.
yeah. All right. Okay. See you.
See you. Thank you, everyone.